In this segment, we'll look at one more simple combinational circuit called a decoder. A decoder again takes n inputs and produces 2 to the power n outputs, where each output line corresponds to one combination of the inputs. And that corresponding line becomes a 1, all others become a 0. What does this mean? Let's say I have 3 inputs, 2 to the power 3, which is 8 outputs, D0, D1 and so on up to D7. So if my input combination is 0, 0, 0, then the corresponding output line D0 will be a 1. All others D1, D2, D3 up to D7 will be a 0. Or for example, if my input combination is 1, 0, 0, which is the equivalent of 4, then D4 will be a 1 and everything else D0, D1, D2, D3, D5, D6, D7, all of them will be a 0 and so on. So that is what the basic structure of a decoder is. So how do we construct expressions for these outputs in terms of the input? For example, if I take my D0, I want D0 to be a 1 when all 3 are zeros, and at all other cases I want it to be 0, right? So again, what we do is, again ultimately the aim is you want to express the outputs in terms of the inputs. So we start by drawing a truth table. So what this table says is, for each combination of inputs, which of the lines is going to be a 1 and all other lines are going to be a 0. Which means when I have xyz as 0, 0, 0, I want D0 to be 1 and all others to be 0. And it also means for any combination of xyz except 0, 0, I want D0 to be a 0 for all the other 7 combinations. And the same rule applies for each of the di's. So now what do we want to do? First of all, we want to get an expression for each d in terms of xyz. And the approach we are going to use here is similar to what we did in multiplexers. So wherever you have a 0, you express it as the complement of the corresponding variable. Wherever you have a 1, you express it as that variable itself. For example, here, if you take x dash, y dash, z dash as equal to d0, you will see that for 0, 0, 0, you will get the value to be 1. And for any other combination of x, y, z, that value will be equal to a 0, which is precisely what we expect from D0. So what we're going to do, we're going to express D0 as x dash, y dash, z dash, and get x dash, y dash, z dash. This is my D0. This is my first output. If you're wondering how this happened, I would urge you to revisit the video on multiplexers and demultiplexers first, and then again come back and take this expression, draw a truth table for it for each of these values of x, y, z, find out what the corresponding x dash, y dash, z dash value will be, and you will see that only for this assignment it will be equal to 1, for everything else it will be equal to 0. And what is the trick to do this? Wherever you have a 0, you replace it by a complement of the corresponding variable. When you have a 1, you express it as that variable itself. For example, here it will be x dash, y dash, z. That is what our D1 is going to be. X dash, y dash, z. That will be D1. This one is going to be x dash, y, z dash. X dash, y, z dash. This is D2. And similarly, you will draw for all up to D7. D7 is going to be x, y, z. So when you draw for all values, that is what your decoder looks like. So this is a very simple topic. To give you a quick recap, it takes n inputs and gives you 2 power n output. So depending upon the combination of input, the corresponding output line will be a 1. Everything else will be a 0. So how do you figure that out? You draw the truth table as usual, and from that you make these expressions. So for any of these expressions, if you take, if I am saying its D0 is represented by x dash, y dash, z dash, then only for this combination 0, 0, 0, this gate is going to give me a 1. For any other combination I take, this will be a 0. And that is precisely what we expect from a decoder. So how do you figure out those expressions? That is the only catch here. Again, so if it's a 0, it's the complement. If it's the 1, it's the variable itself, and they're all connected by AND gates. So that is decoder for you.